In this video, we briefly review our newly published paper titled Model of Cluster of Quark Stars and Exotic Matter. In this work, within the Starobinsky framework, F of R equals R plus epsilon times R squared, we investigate how dark matter affects the internal structure and stability of a spherically symmetric cluster composed of strange quark matter stars. The motivation is the following. Star clusters are key astrophysical systems for understanding galaxy evolution and mass distribution, and the dynamical role of dark matter on these scales has long been discussed both observationally and theoretically. We model the system as spherically symmetric. We define the interior geometry using the line element given in equation 7. Here, lambda of r and nu of r are functions of the radial coordinate r. We then adopt the Tolman-Kuchowicz ansatz and use boundary conditions to fix the model parameters and obtain a physically acceptable interior solution. Next, starting from equation 8, we rewrite the f of r field equations in an Einstein-like form. In equation 9, we specify the energy-momentum tensor and define the pressure anisotropy as delta equals pt minus pr. The key point is that, since the ordinary matter and dark matter contributions are treated together, we express the G00, G11, and G22 components, equations 11 through 13, in terms of effective quantities, namely RO effective, PR effective, and PT effective. This framework underlies the physical results we present next. Let us now turn to Figure 1. The density and the two principal pressure components, the radial pressure PR and the tangential pressure PT, are shown as three-dimensional surfaces as functions of the radius r and the Starobinsky parameter epsilon. The overall trend is clear. The quantities are maximal near the center and decrease smoothly as r increases. The parameter epsilon changes the overall scale of these profiles, with a particularly noticeable impact in the core region. Table 1 provides a numerical check of the energy condition combinations. In general, the NEC, WEC, and SEC are satisfied, while sign changes in certain RHO-P combinations indicate the possibility of DEC violation. Figure 3 summarizes the force balance behavior. While the outer regions appear more regular and closer to equilibrium, the effects become sharper toward the core. The interpretation is that, as the effective dark matter contribution increases, the central region becomes more fragile, whereas the outer layers can remain more quasi-stable. To conclude, this study suggests that the dark matter effect modeled through high curvature corrections does not only rescale the internal profiles, but can also influence equilibrium and stability more strongly in the central region. Thank you for watching. Please subscribe to our channel to avoid missing more paper reviews and in-depth content.